All right, welcome everyone to Wednesday, July the 3rd, 2024. This is 7 p.m. here or 7:15 p.m. rather, in California. Very, very hot day, actually, one of the hottest days we have had. We have had close to 100 degrees, which is very uncalled for in California, to put it mildly. So the topic today is grokking. There is a phenomenon in neural networks which for which we don't seem to have a very clear explanation. It is still shrouded in mystery. Researchers are beginning to nibble at it and understand parts of this phenomenon. But no one seems to be 100% sure that we have understood what this phenomenon is. So I'm going to go over this phenomenon carefully, explain what it is, and then take you through a successive journey of what people have found about this phenomenon. So we'll sort of retrace the history of discovering this phenomenon and where we are at the state of the art. So, for example, this paper for today that we are doing, it came out on June 5th. So, as you can see, it's barely less than a month old, and it really uses this grokking phenomenon to great advantage, or whatever we understand about grokking to great advantage. So what is grokking? Grokking, like double descent. So I'll talk a little bit about double descent because some people believe the two are related. Some researchers believe that these two phenomena are somehow related. There is, about neural networks, there's something quite strange that people observed. That people are asking, is it also true beyond neural networks? Do we see that, for example, in classic machine learning models too? And there is some indication that it may be true beyond just neural networks, but certainly true with neural networks. So there are two phenomena that I will talk about, which sort of we don't understand. One of them is called double descent, and the other is grokking. By the way, there are many things about neural networks that we don't understand, but I will, because these two are sort of considered in some sense related by researchers, I will focus on these. So these two phenomena are double descent and grokking. Now, you may say there are many mysteries about neural network, and that is fair. And why would I pick these two? That should become clear as we make progress in understanding this phenomenon. So first, double descent. Double descent is easy to understand. If you think classic machine learning says, classic ML or statistical learning will tell you a classic plot. It's called the bias variance trade-off that all of you, one would imagine, have been sort of been taught in the first machine learning course that you take. You learn about the so-called bias variance trade-off. And I'm going to gradually chip away at it. What the bias variance trade-off says that as you increase the complexity of the model, and if you look at the error that remains in the best model of that complexity after the training, it will show a particular sort of a pattern of behavior. First thing you'll notice that, and let me use black color because that's what the researchers in the current paper do, is that the total, the bias error, let me just say, the bias error, let's make it flatter. The bias error tends to fall. So one way to think of bias error in a non-mathematical sort of a way is that a bias error comes from a model hypothesis, is a model that is simpler than the ground truth, that is simpler than the ground truth. So to illustrate this, let's say that the data in reality was like this. And I apologize for those of you who are seasoned practitioners in this field. And if you're rolling your eyes, why am I wasting time with this? Just please bear with me. So you realize that if you looked at this data, then a straight line approximation to this data would go like this. And you can clearly see that this model, the straight line model, has significant errors. These errors are because the basic hypothesis, a straight line, a relationship between input and output, is overtly simple, right, compared to the ground truth. What is the ground truth? The ground truth model would be a ground truth representation is probably a function like this, like a sine wave function. So you can do a parabolic function now, a quadratic function. You could do, let's say, something that is like this. Let me do this. Something like this. And that would probably have less of a bias error, but still has an error. But till you get to the green line. But beyond the green line, let me draw those ones in blue. If you try to find more bends in the data, suppose we are doing polynomials, suppose you do like this. Obviously, the blue hypothesis or blue model for the data is overtly complex. Right? It's too flexible. And what will typically happen is when you have models like this, you say that these have variance errors. When a model is very flexible, obviously what I have drawn is not quite correct. But what it does is it exactly fits the data. So a more correct representation would have been that if the data points were like this, right, a blue model would fit the data like this. And as you can see, it is exactly fitting the data because it's very flexible. So when you train it with training data, it just goes and fits to it. Right? It's too flexible. The only problem is training data is obviously a subsample of the reality. When you then try it against validation data or test data, that model is a disaster. Right? And so you say that the variance error, it goes somewhat like this. And so the total error, which we now should represent with, what would be a good color to represent it with? Let's represent it with red, which is the sum total of these two, therefore goes somewhat like this. And so what you have is a Goldilocks region here. This is the place where this level of complexity here is the complexity which is closest to ground truth. Closest to ground truth. Right? So the hypothesis is that if you take sufficiently, for example, if you take a polynomial basis, the function y as a function of x is essentially theta naught plus theta I, x to the power I, summation from I like this.
Sorry, as if we can't see that. If
Am I
you're
not
writing
sharing my
somewhere,
screen? Oh
you
my
are,
goodness.
but I think if you're writing the equation, yeah.
Is it at all visible? Is my screen shared or not? Yes. No, I think remotely it may not be shared.
I can see it. I can see it now, yeah. Sorry.
Okay, you can see it. Okay. Yeah, but was it visible before or it wasn't visible before?
It was a little delayed for me. Sorry.
No problem. So what we are saying is, if you just write it, for example, in polynomial basis. Now, polynomials are not a good basis, as you know, right? Polynomials are the weakest basis to represent functions. For example, they can't represent transcendental functions very well. You'll need infinite many terms. To be convinced, just think of a sine wave. If you try to write a sine wave in polynomials, you will need infinitely many terms because a sine wave has infinitely many bends, and each bend requires one more degree of polynomial. Right? There are better functions, so for example, Chebyshev functions or whatever it is, different polynomials that you could use. But generally, for intuition purpose, this serves well. So the basic idea or the theory, the classical machine learning said that given data, you should build a model of just the right complexity. You have to find the Goldilocks region of complexity at which the trade-off between the bias and the variance balance. It is a good theory that has sort of served the purpose or gives us a lesson that, yes, we need to be in pursuit of the ground truth, complexity. Problem comes from multiple places, actually. Problem comes, for example, you can have a model with high bias and high variance errors simultaneously. So, for example, if the ground truth, let's say that you're creating a decision boundary and say that the perfect decision boundary is like this. So you realize that this decision boundary has, and let's say that all the points on this side are positive and all the points on this side are negative. And so this is a decision boundary. You realize that in this region, which I've shaded, the black region, you need a model of sufficiently high complexity. So suppose this decision boundary was the real ground truth, right? You would need to approximate it with a complex model. On the other hand, outside this region, if you look at this region or this region, you need a model of not so high complexity. So that again brings up the first complication that you see with a simplistic bias variance trade-off as narrative is that a bias variance trade-off as a narrative is true, but it could be a local phenomenon. Each region of the feature space may require its own bias variance trade-off because it may have its own sort of a model complexity needed for that region. Right? So this is something that we just to remember. Now comes a mystery, which is the double descent mystery. And sorry for taking a long digression. Double descent. The reason is it turns out that double descent may or may not be related to the main topic of today, but many researchers believe that it is related. What you notice with neural networks is, and that, so I will just now draw the main red line, which is the sum total of all errors. What happens is that as you increase the model complexity, sure enough, what you expect happens, the bias variance trade-off. There is a certain model complexity here, but then something most unexpected happens. After a certain model complexity, the error reaches a new minima. If you observe carefully, this minima is actually better than the previous classical minima. So people call this the deep learning region or modern ML. People often use all sorts of terms, modern ML, and this is the classic ML region. And obviously the axis is model complexity. Now, if you're thinking in terms of neural networks, just think of it as number of parameters in the model. That is a very good proxy to think about it. These days, we all talk about 7 billion parameter model, 13 billion and whatnot, 70 billion. So that way of thinking is a pretty good proxy for model complexity. And so what people have observed is something quite mysterious, that if you take a simple enough model, as you make the model complex, you achieve a minimum. You make it more complex, then you start having overfitting. So this is the region of bias errors. This is the region of, in a way, variance errors. That's the way you think about it. More bias errors, more variance errors. But then here comes a mystery. The neural network, after some time, as you make the model complex, but you have to do one thing. You have to keep training the model. You don't stop. You just go on training the model. And after a little while, what you notice is that the validation error takes a sudden dip. And we do know from everything since this mystery is called the double descent, the mystery of double descent. I'm deliberately using the word mystery to emphasize the fact that we don't fully understand it. Though I would say that ever since its discovery, researchers have been sort of nibbling at it, and they have a pretty good sort of chipping at it, and they have some reasonable intuition on what really may be going on. We do, for example, know that the neural network somehow discovers a very simplifying hypothesis, so that most of its circuitry becomes redundant and it just finds some specific circuitry which discovers a simpler model within itself. Okay? That's
Quick
a problem.
question. When you've said that the x-axis is model complexity, is that purely the number of parameters, or is there another complexity elements such as a depth or other elements of the model?
So generally, depth could be considered another measure of complexity. Generally, any one of these measures that you take, you will observe a double descent phenomenon. But if you say that I'm going to keep the number of parameters constant, but I'm going to just shrink the width and increase the depth, then you won't. Then you tend, or to my knowledge, you don't tend to see that. You have to have just a whole lot of weights and biases. So let's say that you keep your, let's take a classic neural net, 512. 512 seems to be pretty popular for a feed-forward layer width. You take 512 and you keep it fixed, and you keep on adding layer after layer, and so you're adding complexity to it, then you will see double descent behavior. Okay. So this is the mystery of double descent, and people often allude to this when people say we don't really know how neural networks work or what really is mechanically, and now I'll introduce a term that is quite important: the mechanistic interpretation of the neural net. What really is going on from a dynamics perspective, we don't quite understand, though it is at the heart of XAI efforts, explainable AI efforts. And explainable AI is, of course, goes to the heart of the AI safety and ethics and bias and all of those bigger concerns associated with it. So obviously these things matter. Now, somewhat related along this line, there was another discovery which people did, and now I'll go back to that discovery because that is grokking. And it is best illustrated with these diagrams. I will just show a thing that people observe, which is most unexpected. There was this work which came out in 2022, early 2022, quite remarkable. You take a simple table of binary operations. So you notice that this is a very simple algorithmic problem. You tell it that you are doing a binary operation, let's say a binary operation between two variables, x, y, and now you put in some binary operation like plus, minus, multiplication, division, or whatever it is, modulo, whatever you like. And whatever the result is, you put it in a table. Right? So let's say X is ABCDE and Y is ABCDE. Now they took this example to illustrate what AA is A, AB is D. So you have to figure out what exactly are they talking about in this. And you leave a few question marks for the machine to figure out. You don't tell it what it is, which particular operation it is. The other thing that they took, which was very interesting, they said that, see, how about doing modulo? So, when you do, we typically do, let's say, modulo 10 arithmetic. What is a modulo 12? We all do that. After it is 12 o'clock, it becomes 1 o'clock, right? 13 o'clock is 1 o'clock. So in a day-to-day life, we do modulo arithmetic all the time. So these people deliberately took a very unusual modulo, which was modulo 97. Why 97? For no particular reason. People have tried all sorts of modulo and the results are still the same. So what if we do a modulo division or modulo addition or something like that? So as you can see, these are very simple operations, but teaching a neural network is a bit hard, these operations. And what they observed is that if you give it data, like for example, just this tiny table of data, it's a very simple table of data. What you observe is you keep running iterations. So the x-axis is the steps. So we remember that and just to remind you that the basic learning loop is for an epoch, and inside that epoch you have another for loop for a mini batch. What do we do? The classic learning loop is that you would do y hat is equal to the forward pass on x, right, on the input, right? Then you would compare it against y, and you would look at the loss function. Loss is the comparison between y and y hat. Then you would back propagate the loss. This is the backward step. And the final step is the actual gradient descent step, which is that a weight, the next value of the weight is, right? Or let's say that the weight in the iteration I is weight in the iteration I minus 1, right? Actually, this paper uses theta, so let me also use theta, right? Minus gradient descent. In the simplest form, right? It's usually, you don't do vanilla gradient descent, you do something more, better, a little bit more sophisticated. For example, momentum-based adaptive gradient descent and so on and so forth. But roughly speaking, these are your 4 key steps. So you have for every epoch, for every mini batch, you call this the step of learning. Are we together? So one iteration, step or iteration, or step. So it is this one thing, this one exercise. I would say this whole exercise is one iteration over a mini batch of data. Right? Now, what this paper is saying is, see, when you start training the machine, suppose you have gone through only 10 steps. So by the way, the x-axis is powers of 10. So remember that this is, in simple language, this is 10. Here is 1,000. Here is 1,000. And here is million. Million here, this point. Right? This is 1,000. This point is 10, 1,000, and million. So what it says is, if you look at the accuracy, when you have done only 10 steps, both training laws and validation laws, they are pathetic. Right? Then somewhere along the line, this machine is beginning to, at about 100 steps, you can see that the training loss begins to decrease. Sorry, accuracy begins to increase, not the loss. I should revise myself. This is accuracy. The accuracy begins to climb, and it suddenly climbs here, which means that the loss is decreasing, and it reaches close to saturation, 100% accuracy. But if you look at the validation loss, it is still practically zero. I mean, accuracy is practically zero, loss is high, accuracy is zero. At that moment, what would be? So suppose I look at this stage, your inference would be, at this moment, the machine seems to have memorized the data. It has overfed the data. The only times that it can get it right is when you give it a training data as input, and it will give you the right output. But for anything else, it's a disaster. But what they noticed, and this was a surprising thing they noticed, that, you know, most of us would have stopped at this level where I'm drawing the black line, right? Or even before that, you would have stopped somewhere here. You'd said, all right, this model is too complex. It has overfit the data, or there are only two ways to fix it. Go get more data to prevent overfitting, right? Or do some massive regularization, or do something, right? Or simplify your model. But what they observed is that if you just keep running your machine and keep training it over and over and over again, and you go to close to 10,000, 100,000 iterations, do you realize that this is a very high number of iterations? And it may beg the question, why in the world are you wasting CPU cycles doing that? Well, these researchers chose to do that. And what they noticed is something quite surprising. You notice that this green line, which is the validation accuracy, shoots up, which means that the validation error is shooting down. Validation loss is shooting down, right? Accuracy begins to climb up. Now, when accuracy on validation data climbs up for a model, you realize that it is actually learning at that time. It's not memorizing. It has learned to generalize, somehow generalize from the data to the right hypothesis, to the right, for example, in this case, the right binary operation, or the way to do modular arithmetic, and so forth. Does that make sense, guys? There is no other, I mean, you can't, this green line going up, this particular green line going up is a clear indication of generalization in the model. It has learned it, or it has learned to generalize. Learning has taken place, which wasn't taking place before. And if you really look at the gap between these two, this is a phenomenal gap. It manages to learn. See here, it manages to learn in just somewhat 200-300 steps, give or take. And this, it manages to memorize the data. It has begun to memorize the data and overfit to it in just a few hundred steps, isn't it? On the other hand, it has finally understood the real binary operation, or whatever the real generalization of the data is. I built a correct model at close to a few 100 million steps. What a huge gap between 100 and 100, sorry, not 100 million, 100,000 steps, right? And it reaches saturation around 1 million steps. So that is the phenomenon of grokking. And this paper goes into a lot of explanation and hypothesis and so on and so forth, which we won't go into. But the interesting thing that is worth bringing up is something they observed. And I'll just focus on this picture. This one is modular 8 arithmetic. Modular 8 arithmetic, or something like that. I think so. Yeah, element. The color shows the residual of each element. Modular 8. So it is just doing modular 8 of numbers. But do you notice that if you look at the logic, so you have a neural net with lots and lots of things happening before that. But if you look at the final layer, logics, and you represent them as a vector, right? So these things, this layer forms a vector, a hidden state representation. If you take that hidden state representation, and well, of course, you want to visualize it in 2 dimensions, pass it through a TSNE. TSNE is a dimensionality reduction projection in 2 dimensions. When you do that, do you notice this beautiful circular pattern, right? And a circular pattern, the first thing you say, oh my God, it has figured out the clock, because modular is basically clock arithmetic, isn't it? So think about it this way. You have 12, 1, 2, 2, 3, all the way to 11, 6, right? So suppose you want to add, you have 2, and you want to add a 10 to it, or 12 to it. Let's say 12 to it. So what will you do? You'll go back and come back here, right? Or 11 to it, then you'll end up here. So it's basically, you need a clock representation somehow, and you begin to get an intuition that what is this thing up to? Is it beginning to understand it somehow? Right? But this paper stops there, and it actually doesn't make the statement that I'm making. I'm making a much stronger statement than what the paper makes. But it does mention that you tend to see some things like a circle, right? Very, very interesting. Then comes the next paper. Where am I? That is it. People asked, what really is going on? This paper tried to give a mechanistic interpretation of what really grokking is up to. Because people are, it's a big mystery that needs to be solved. And as this paper moved on, what it found is literally unbelievable the first time you realize that it's doing it. You ask it to do modular arithmetic, and what it does is it realizes that I need to do arithmetic on a circle, right? And what it does is it effectively starts doing trigonometric representation of numbers, right? And so what it means is there's a lot of mathematics here, but what it basically says is that if I take a rotational velocity or angular frequency, rotational frequency, which is what maps to the notion of modulo, where am I? Modulo thinking, a modulo. Right? So I'll just give a hand-waving argument. Suppose you have p numbers, you're doing modulo p. You would agree that somehow it has to do with the rotation by p, right? Frequency p or something like that, right? You can do that. So, for example, if you do 2 pi over p, then what happens is any value that's a multiple of p. Let's take any value. Let's take p is equal to, what should we take? Let's say 10. P is equal to 10. So we put 2 pi over 10. And now, suppose you do two additions, a plus b. Just try to do anything. Pick a number. I'll just pick a number 5 plus, so let's take a few examples. 5 plus 5, right? 7 plus 8. Let's take these two examples, right? So in the case of 1, 5 plus 5 is 10, right? So suppose this maps to 10 is equal to 10. So what will be 2 pi over 10 times 10? It will be just 2 pi. And what is the cosine of 2 pi? Or cosine, same as cosine, it's 1. Right? It is the maximum possible value, isn't it? And so think about it this way. What it can do, and the way this machine learned to do it, is that it would take a certain bit of logics, let's say 1 to 10. 1, 2, 3, to 9, all the way to 9. And it will say that this is your value C. And it will say A plus B minus C. Right? Now you realize that this cosine, if I do cosine of this, A plus B was 10 plus B minus C. Now, 1, by the way, 0, I should also put 0 here. 0, 1. Now, which value here will maximize A plus B, like this whole value, the cosine of A plus B? You realize that you want either 0. 0 would be a good value, isn't it? 5 plus 5 minus 0, then you would get the cosine of just 2 pi and it will be 1, right? So it figures out beautifully that all we need to do is for all of these numbers, I just need to do this kind of arithmetic, right? Which is going around in cycles. And the amazing thing is that this machine, unbelievably, it creates embeddings. It creates an internal, this embedding representation that it creates is literally this for the inputs. It creates these representations of it learns to create this representation of the input, right? When grokking happens, like when this, a point is reached at which the machine, so remember what we said is, let's again keep using the accuracy as the y-axis and iterations as that. So remember the old picture was that the training accuracy shoots up very fast, whereas I should use another color. Let me use this. The validation accuracy reaches up much later, right? But at this moment, when it has, you can say the machine has grokked. The word grok means to understand. And in a way, when the machine has really understood the data deeply, you will note what they found is that this is what it was doing internally. It's just absolutely beautiful when you think about it. That when it is grokking, when it is doing that, it has somehow managed to learn to do essentially this, right? It has learned to do its Fouriers, it has learned to do trigonometric relationships, and this is what it is doing to compute the modulo. Right? So this was another breakthrough that they found, and they realized that now we understand, and this was a big step in grokking, understanding grokking. It's a mechanical understanding in some sense of how exactly is this machine thinking in solving the problem. Does it make sense, guys?
And this is for all problems?
Yeah, so that's a very good question. So hold that thought in your mind, right? So then once this was discovered, it generated quite a bit of interest, and it is not too far off. You realize that this is just a few months ago that it was discovered, and this is at the UC Berkeley, and then came. By the way, this particular paper, I'll strongly invite you to go and look at the website that they have. They have a wonderful website, the grokking paper, and you can play and engage with it. There's also a GitHub and all of that, but they also have simulations that you can go and little experiments you can do, and you can play with it. I won't go over the main paper because we need to cover a lot of territory. So I'll now move over to the next paper, which is the question that here Albert asked. Well, this is fine for simple examples, simple data sets like modular arithmetic. But is grokking as a phenomenon actually seen for real data sets? MNIST, sentiment analysis on the IMDb and whatnot. Right? Will it actually work in real world situations, computer vision and natural language processing? So this was this other paper, the OmniGrok paper, which was interestingly from the physics department at MIT. Right? So a bunch of physicists, and you can see in this paper, they come up with a very physicist reasoning about this whole thing. So this paper is about two questions that they ask. These two questions. Why is it that the grokking takes place many steps later, almost 1 million steps later than overfitting? Right? Why is it so delayed? That's a mystery, isn't it? And the second question that it asks is the prevalence of grokking. Right? How prevalent is grokking? Does it only work on these toy data sets, or is it true for real world data sets? And to both of these, it comes up with an answer. It says that grokking is caused by a mismatch between training and test loss landscape. So it goes into an explanation into the loss landscape, which is very interesting. We'll delve into that a little bit. And then the second question, it does come out with a resounding yes, because they show that grokking is observed in real world data sets also. Right? The same behavior. So this is a good takeaway, because if this was not true, we might as well have ignored grokking as a plaything for the academics. But it is a real thing. Now, why? So it puts a pretty interesting perspective. Today, we have very large models. We train them just enough to get good results. Right? We do know that these machines, these large language models, etc., there is a whole lot of memorization going on. And there is a whole lot of generalization or learning going on. But the more you train, the more the learning will happen. But we never really, you can see that the loss is still going down, but people say it's good enough and they release the model because there's a fierce competition to release better and better models. The question does remain, and many people have asked, shouldn't we train smaller models with a whole lot more data? And all of those conversations are in progress. So in that, this grokking is really in perspective. It begs the question, did we ever wait for the grokking moment? Right? In the model, did we wait for that? Anyway, that's something to think about. Now, one more thing I must mention, which was in the previous paper. The previous paper mentioned that learning takes place in 3 steps. First step, which is obvious, which is dead obvious, and you can see the neural network will do memorization. It will just go memorize it. So these people call the phase transitions. It's a very physicist term. Transition. Am I writing it right? Hopefully. Transition. Transition. First, the phases are, you have memorization. The machine just memorizes the input data. You can see that memorization in this part, right? Suddenly. And your validation error is still here. So you can literally say that this is the part at which memorization, this is the memorization phase. And then what the researchers found is that while it looks actually that the machine is not doing anything, because training data has stopped and the validation is still going flat, right? And the training data is, of course, saturated up here. This is accuracy. This region where nothing seems to be happening, actually, this is when the machine is learning to generalize. Something is happening internally. And the previous paper actually shows you that it is happening internally. Learning or generalization is in progress. So actually, the real learning is taking place there. And then after it has come up with a simplification, what it does is, then comes the cleanup phase, actually. There comes a cleanup phase. Cleanup phase, which they find very interesting. What they find is that once the machine has understood or created a real model of the data, it still has a work to do. It has to forget the memorization, right? It has to throw the memorization out of the window. And now it has generalized, because remember, memorization is now hurting you at that particular moment. You have a model. Right? So as it forgets the memorization, this upward climb takes place. The accuracy begins to come up. And that's a very interesting observation that the paper made. So we talk about 3 regions. The first, I'm sorry, I should not use this color. The first region is the memorization region. The second region is actually the real learning region, where the machine is learning, but it appears it's not doing anything, right? It would, to the outside observer, it looks like, okay, it's just going nowhere, but it's actually hunting for a good generalization. And once it has found that, the observed accuracy on the validation set still doesn't go up. It begins to go up. After it does, it gets rid of the cleanup. Right? I suppose I'm exaggerating it a little bit. Let me be more realistic. It goes like this, right? But most of the gains come when it throws memorization out of the window and it relies on the generalization. So it's a very interesting topic, the fact that these things are happening. And then comes the crux of the main paper that I was leading you guys towards. And by the way, this paper talks about this OmniGrok paper. The current paper finds something very interesting. It says that actually, when you look at the double dip, which looks very mysterious, remember, to remind you, double dip was this, right? Or let me simplify it. Double dip was, you go to a new minima of loss, which is much lower and better, right? At steps, at complexity. So if your x-axis is complexity, y-axis is loss or error, then you will see something like this, right? But on the other hand, and there is something called reduced weight, normalized weight or normalized weight. they found, and it is the discovery of the so-called Goldilocks regions. Right? This paper puts a lot of emphasis on weight decay. What it says is that there is this green region of weights in size. The the weights and bias, the words parameters. If your parameters are too small, you're inside. If your parameters are too big, you're outside. But there is a Goldilocks region of the value of weights. Right? It is almost like you have to discover two things. What is the radius of that circle, approximately, or that sphere or hypersphere in the weight space? And once that is discovered, the only thing left to discover is that what is the, for every weight, what is the angle? So you need to know the magnitude and the theta, isn't it? The absolute value and the theta. The right absolute value, go ahead.
So the previous image, what was the last phase called? Generalized phase? So one was a cleanup.
The so,
last.
No, so first is memorization, then is generalization, and then comes the cleanup phase. Last is cleanup.
So, and once you finish the cleanup, what happens?
That's it. Now the machine won't learn anymore because it has learned to generalize from the model, from the data.
Called the generalized phase at the end. Once it's done the cleanup.
Then you say that it is generalization is complete.
Okay, generalization.
Complete, yeah. That's what you would say. So now this is called the Goldilocks. So I will just mention this because these terms are often talked about these days. Goldilocks region. Of course, as you know, that comes from the story of Goldilocks region. That you have to find, first task is to find the Goldilocks region for the weights. That comes to proper weight decay and regularization. So then the only problem left is for each weight to find its angular position in that hypersphere. Right? That's all it is. So these are good solutions. Solutions outside the Goldilocks regions are overfit. Solutions inside are sort of underfit. Now, what happens is this paper hypothesizes. It's just a hypo. I don't think it completely proves it, but there's enough reason, persuasive argument. What it says is that if you look at the loss with respect to these normalized weights, the training loss, of course, goes like this. It flattens out. Look at the orange line. It flattens out. If you don't regularize. If you regularize a little bit, it's a small. If you regularize a large bit, it's this. But if you look at the test loss in the beginning, by the way, here the x-axis is weights now, the size of the weights. It's not the number of iterations. You notice that what they are saying is that test loss rises. If you start out with high weight, see, suppose you start here. You initialize your machine with these weights. What happens? Just take this. If you compare to small with small initialization, do you see that the gradient is much more steep here? You can quickly learn. On the other hand, here you'll creep your way forward. So what will happen is your training loss is already very small, but your test loss will creep its way gradually, slowly making progress to the Goldilocks zone, right? So it's their way of trying to interpret and say, maybe that is what is going on. And that's what explains that for a long time, it seems that the machine is not improving at all. It is improving. You just don't see it. Obviously, this narrative is completely compatible with the previous narrative, which says it's searching for a better generalized model. And they have reinterpreted that in terms of weight normalization. And they call it the LU mechanism. The fact that test loss has a U shape and the training loss has a L shape. This is a L shape, whereas the test loss will have a sort of a U-shaped test loss. So the LU mechanism. So anyway, I'm covering over a vast amount of literature here. I will now come to finally where we want to end with today, which is something really interesting.
Just a couple of questions, if that's okay,
Yeah,
based
please.
on what you have covered. So first thing is there like in either of these papers a snapshot of t-SNE embeddings and how it looks like through the course of these three phases, And is it only in the cleanup phase that nice generalization or the nice t-SNE embedding arises, or it's starts
No, it's a
emerging
slow
as
emergence. And that's the nice thing. It's a slowly you see it emerge.
I
And
see.
there are visualizations, not in this. I believe in the last paper, in the last one that you'll see in there. And by the way, most of these researchers, they have done a lot of effort to put up, not just write the paper, but and release every code in GitHub, but they have created beautiful visualizations in their website that you can play with. And in one of them, you can literally see how the weights gradually zoom into the right place. Yeah. So what it is, see, the big message behind all the research in grokking is that they are saying, see, between these two regions, right, when the training data is overfit, and this is the test validation accuracy, and the test, train accuracy. In this region, all of these steps that are happening, what really is going on? All of this research is trying to find that, right, and explain that. And very persuasively, they're beginning to show what really is happening under the curves, right? So this is not a dead zone, but it is a zone in which a lot of activity and improvements in the model are taking place step by step, and they want to show it to you. So I would encourage you to look at those visualizations. And now comes the interesting question.
Hey,
This,
Asif, just one more question, if that's okay. The thing that you showed about all the weights lying on the surface of a hypersphere, is that kind of a um, universal thing? Because at least I haven't seen that all the weights is lying nicely on the, meaning that all of them have some specified given norm kind of a thing, and all they have to do
yeah,
is lie on the surface. Is that more universal, or this is
yeah,
specific to some
no,
of
no,
these
no.
problems?
So you see, you have to know that the way it has been defined is with a normalizing metric. So you have to at every given moment there's a particular normalization they do every time they compute the weight and they do the learning step. They renormalize it. But if you do that, but in the weight space, right, these are normalized weights. But yes, with what they are finding that is with neural networks, you do seem to have a Goldilocks region.
Got it. Thank you.
Very interesting, very interesting fact that such a Goldilocks region does exist. So now comes the interesting thing. Let's bring all this theory to something practical. The practical problem is this. Training is very, 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 very expensive, right? You go so the way typically it would happen is researchers will go to the company and they would say, oh, we want to train a model. Can you please give us 1,000, let's say, let me exaggerate it. Can you please give us 1,000 GPUs? Company will say, no. Well, 500 GPUs. No. Well, 100 GPUs. Okay, maybe. And then they say, okay, we're giving it to you for 1 month. Let's say, I'm just sort of making up a story here. We'll give it to you for a month. You say, okay, can I have it for a month? And the company will say, month? Forget about it. We'll get it for 1 week or something like that. Right? Most real world situations are like that. Only big models like the GPTs are trained for months. Most of people, like you and me, when we humble people who go and ask for computer sources, this is what we get. They chop off a few orders of magnitude in number of GPUs they can give us. And if you ask for 1 month, they'll give you 1 day. Right? So then what happens is, and that's the crux of the problem. Suppose again, let's take the accuracy as the y-axis and the number of iterations. So you realize that iteration t is a proxy for time itself, isn't it? How much time you get to train the model. Suppose you know that, and again, let's go here. You know that in the beginning, your machine has overfit and your validation loss is still here, right? Your tragedy is, and the practical reality is, this is at this time, You're out of time. Time has run out. Right? Because that machine is expensive and it has to be used for something more useful than just seeing a useless model whose validation accuracy continues to be low. Does that make sense, guys? So if you do believe that grokking will take over at some point, the problem is you don't have time for grokking. So let's say that grokking takes over at this time, beyond what your budget is, time budget is. What would you love to see? A mechanism, you would love to see a mechanism that pulls this curve inwards. Let me take a less fat line. You would like to see some machinery, some technique that sort of makes this possible, because this is within your budget, isn't it?
Mm-hmm.
You want the grokking to go from this to this, right? Except that this is, because the axis is orders of magnitude, this is 10, this is 100, this is maybe 1,000, this is 10 to the 5, whatever, 10 to the 8, whatever, 100 million steps or whatever. You want grokking to get pulled in. It must kick in faster. And therefore, the title of this paper, a very practical thing, GrokFast. How do you accelerate grokking? Do you see why it is of great practical importance? You must grok fast, otherwise your project is over.
Quantized grokking.
No, quantization doesn't help. And what they found is it is simplicity in itself. Actually, they found a way that is barely 8 or 10 lines of code. In your typical for loop, the training loop that you write in PyTorch, you just need to add 3-4 lines more. Imagine the sheer simplicity of it. You need to just add 3-4 lines. But those 3-4 lines derive from a beautiful idea that these people have. They make a hypothesis. And so let's finish our reading today with this paper and its introduction. And I'll just do, once we read the introduction, that is all we need to do. This is the algorithm. There are more details in it, but I think we can cover it pretty quickly because it's a simple paper with great results. I'll read the abstract. One puzzling artifact in machine learning, dubbed grokking, is where delayed generalization is achieved 10 folds of iterations after near perfect overfitting in the training data. Focusing on a long delay itself on behalf of machine learning practitioners, our goal is to accelerate generalization of a model under grokking phenomenon. By regarding a series of gradients of a parameter over training iterations as a random signal over time. And this is the beautiful idea. And you can, by the way, do you notice how gradually physics ideas and things from electrical communication theory and information theory are beginning to creep into this thing? Most computer scientists don't do Fourier transforms. Right? But you will see that this argument is based on something pretty beautiful and simple. And if you know Fourier transforms, this will look pretty obvious to you. So what it is saying is that we are going to look at this of some thing, gradient. So remember, where does the gradient come? Theta t is equal to theta t minus 1 minus alpha. Gradient of some function, loss, whatever it is that you're looking with respect to theta t minus 1. Are we correct, guys? Right? This is the gradient. So now this gradient, this is the raw gradient, but when you use smarter optimizers, let us say that you are using Adam or something like that, you would sort of amplify this equation by saying t minus 1 minus alpha minus some gradient, some update function, plus some update function, which is a function of the gradient at time t. It's a gradient. It could be, as you know, I'm just writing the gradient. It is not just the gradient. Momentum-based gradients are complete functions. So what it is saying is that you're updating to the previous value, you're adding a certain update, right? So you're saying theta t plus 1 is theta t plus some update at t. That update at t is a function, is some function of the gradient at t, the gradient value of t at the tth iteration. So I hope these equations make sense, guys, right? You're saying that the new value of a parameter is the old value and some update, which is practically the definition of an update, right? And that update itself, we do know, is some function based on Adam or whatever it is you're using, more sophisticated variant of the plain and simple gradient descent, right? Momentum-based gradient descent. It is some function of the gradient. This is the gradient, right? Some linear function of the gradient. So far, so good, guys? And now what they're saying is that if you look at the gradient, GT, and consequently UT, both of this, if you just plot at G0, G1, G2 at time intervals, iteration intervals. And so here comes a beautiful intuition that people are using more and more. See, iteration T and time T, you can think in the limit of very large number of iteration that T is practically a continuous variable, isn't it? But anyway, it's like time. So people often think of iterations as time, especially the physicists tend to, or electrical engineers tend to think like that. So there is G whatever, and finally GT minus 1, GT will be there. And likewise U0, etc. They'll depend on these prior values, right? Now it says that if you treat it as a random variable, so then it will show some some behavior like this. I'm just making a guess, right? The gradient. And so I'm giving you the main idea of the paper. The gradient, GT, this is T, this is GT. Suppose it looks something like this. Right? Now, just looking at the signal, can you see something? It has a slow moving component, and it has a fast moving component, isn't it? There's a high frequency component and there's a low frequency component. Well, I have deliberately created it. I don't think the real life is as simple, but just for the sake of explaining it, right? You can go to your mind and say, hey, this is what I see is happening. The gradients are going like this, right? Or the update functions are going like this. Like through it, you feel that somehow the slow moving. So when you do the way the sort of smoothing out of it is more meaningful than the jitters. That's the intuition behind it. Would you agree, guys, that the smoothing of it is somehow very relevant compared to the jitters? So if we could, so the main hypothesis that this paper makes, it says that that smoothing out, and there is a terminology that people use, especially in electrical engineering and physics. They say that if you decompose a signal in its frequency components, frequency domain, or another fancy word of it is that if you do a spectral decomposition of, which is another fancy way of saying, let's just break it up into its frequencies, you will see that there will be a low frequency component and a high frequency component, many high frequency components, right? And some in between components. Are we together? Does it make sense, guys? And the machinery that helps you do that is called the Fourier series and Fourier transform. Right? And there is a certain amount of machinery. So here it is. If you, for example, want to take the discrete Fourier transform of this update function, you multiply it by e to the minus omega t. Why you do it? Well, you have to go into the mathematics of it. But just take it as a fact that if you do this thing, which most of you may be familiar with, you may have picked up in engineering, but if not, just ignore it. But just say that there is a mathematical machinery that extracts the frequencies from the signal. Right? So if you do this and you go into the frequency domain, then you can pick and choose which frequencies to keep and which to sort of which to amplify and which to ignore, right? Or not amplify. And the same thing, if you do it with update, because update is related to gradient, then the gradient itself has frequency components. Then comes the main hypothesis that this paper had, which is this. Our main hypothesis is that amplifying this low frequency component, GW, accelerates the speed of generalization under Grokking phenomenon. So guys, this is a pretty astounding statement. It says that all you need to do is you need to amplify the low frequency component, and then what will happen is this big practical result will come out. Your grokking will get accelerated. It will happen much sooner than the baseline. Right? Now, what is the intuition behind it? The intuition, the reason it happens is, like you can see that the low frequency component somehow is more informative. So we amplify it. And therefore, the main model, this picture with which this, and nowadays it's very customary for research papers to start with the key ideas on the very first figure. And this is the key idea. Let's look at this idea and see what it is saying. Right? So guys, what is our main job? We, at any given step, we always update the t plus 1 is equal to theta t plus some update function, right? Some update, which is based on the gradient. Update t, which is equal to some function of the gradient at t, right? Some function of the gradient. Are we together, guys? This is your learning step. This is your step of learning in machine learning, in neural networks. This is your classic gradient descent amplified with all the fancy optimizers, but this is it. So what you do is you feed it data. Remember, what do? Forward pass, compute the gradients. Then you have computed the gradient of the loss, whatever it is. Then what it says is something very interesting. You treat the gradient as a signal, and what you do is you amplify. So here's the thing. The gradient goes in. Normally, if you don't imagine this red component, typically what would happen? A gradient will go into the original optimizer and it will do this step. Right? Optimizer will do, and it will come up with an update without this red component. But what this red component is doing, it is a low pass filter. Low pass filter comes from, well, communication theory, communication engineering. Low pass filter, electrical engineers should be very familiar with it, and physicists. What it does is it amplifies the lower harmonics, right? And one easy way to amplify lower harmonics is obviously take moving average or something like that. But there are many ways to do that, and that is what it does. From this, you extract that and go back and add it back into the signal. So you say, take the signal gradient, and then suppose the gradient is made up of a low component and a high component, right? So what you do is gradient t plus the low part of gradient t. So then what does it become? It becomes, suppose it was this, low plus high, and I'm obviously oversimplifying it, high, and then it becomes a plus low. Do you see that, guys? If G is some low part and a high part, or maybe some medium part also, right? What you're doing is this. So it becomes twice the low part plus, let's say, the high part. Grossly oversimplifying it. But by doing this addition and taking the low component, low harmonics, and adding it back here, I'm just boosting the lower frequencies of the gradient, right? That's all. That is all. And it is saying the big hypothesis that it makes is this hypothesis. Our hypothesis is that amplifying this low frequency component of the gradient accelerates the speed of generalization under the Grokking phenomenon. So you have to, you compute the gradient here. Obviously, you go to the frequency domain, amplify the low frequency, pass it on. That's what the low pass filter does, and so on and so forth. So this is the gist of the paper. There's a bit of mathematics on how to do that. I will skip over it because many people may not have background with that. It's very simple. And so they go through a successive sophistication of their method. The first sort of a low pass filter they implement is using literally the pi function, like this, minus half, half. Anything in between has value 1, otherwise it's 0. It's like a two-step functions back to back. This is the Heaviside pi function. Again, electrical engineers, signal processing, you come across this quite a bit, otherwise not. It's a way of saying within this window, I'll average it. These last few signals, I'll average it. Well, you know, that's not a very bright idea. The problem with doing this windowing thing is, and this was their first iteration, they're doing that. Now, with this algorithm, the problem is to compute this, to treat the gradient as a signal, you need to keep stock of all of the gradients, right? You have to remember Z0, G1, GT. That's how you're going to compute the Fourier transform. Otherwise, you can't, right? So you need to keep all of them. So let's look at the limitation of this paper. The first thing they point out that, oh my God, you don't have to store just one gradient. You have to store all the gradients. And those gradients become more and more and more and more, isn't it? And you have to store the updates, well, so likewise, update T. Now, that is not something that you want to do. So one way that you could do is simplify it is to moving average, you know, that is something moving average. You could use something like a very simple step function and take a window, and within that you can compute you can keep sliding the window and keep finding the moving average. You could do that. That still doesn't quite solve the problem. Then the next step you could do, it makes it better, but next you can do is use exponentially decaying. So there is another version of it, exponentially decaying moving average. So that is why the word MA here comes from that. And then the exponentially decaying moving average. Now, those of you who know what exponentially decaying moving average is, what you will say every time T increases. So look at this. Let's ponder over this function. Lambda is some hyperparameter. Let's ignore it. Alpha is, let's say, I'll take the value alpha is equal to 0.9 for the sake of argument. Now, 0.9 to the power, when T is equal to 0, what is the value of alpha T? At T is equal to 0, alpha T would be 0.9, right? T is equal to, T is equal to, actually, it would be 1. It would be 1 at, let's take T is equal to 1, actually, let's not take T is equal to 0. It would be alpha. T is equal to 2, it would be alpha square, and this would be 1 minus alpha. And this would be alpha square 1 minus alpha. So this would be what? First was, it was 0.9 times 0.1. And now it will be 0.9 square times 0.1. 0.9 square is 0.81 times 0.1. So this final factor 0.1, 1 minus alpha is constant. Let's ignore it. Focus on this part. What does it do? 0.9, 0.9 square, 0.9 cube. You see, this is 0.9, this is 0.81, this is 0.7, give or take. It is shrinking.
It's exponential decay. Yeah.
It's exponential decay, right? And so if you take that for the value of the previous gradients, like how important is a particular gradient, right? In computing the current gradient, then you could use that. But now I would just like to focus on this little bit of a detail on the actual algorithm. You will see that the algorithm is simplicity itself. It's very simple. What they are saying is, in the inner loop, for a given time, see, you're going to compute the gradient anyway, right? You compute the gradient. What they are saying is, insert the gradient into a queue. Maintain a queue, list, Q, and actually, if you look at the implementation, they use a DQ in the simplest case, for those of you who are interested. And so you insert the gradient, G0, G1, you keep track of it. But then what do? Next step, you again see, it is just simple. The only extra step you insert is these 3 steps. Save the gradient. When you don't use the original gradient. Instead, you use the gradient modified with lambda average cube. What it does is, it sort of amplifies the low frequency part of the gradient. because averaging does what? Smoothing. Smoothing is what? Keeping the lower frequencies amplified, right? That's what you're doing. And then go ahead and do your update function. So when you do the update, you're doing the update not using the original gradient, not using this, but using G hat. That's all. And then the rest of it is, of course, exactly what you do in gradient descent, right? So they have just inserted these two steps. Really, the meaningful step is these two steps they have inserted. You see how simple it is? And yet, when you do only this much, and then this is a little bit more sophisticated, it is using exponentially decaying sort of a moving average and so on and so forth. But let's look at the results. Then they also do one more thing, weight decay. Remember the previous paper on OmniGrok, what did it say? The weight should shrink and then go into a circle, into a sphere, a decay. So basically think weight decay is regularization. L2 regularization is the simplest way to do weight decay, L2 reg. Right? All of you, I hope, are familiar with L2 regularization. Is the first regularization technique you learn in machine learning. So I will skip over most of it, but look at how dramatic the results are. It's just unbelievably, like first time you see it, it strikes you. The first time I remember reading the paper sequentially, and wow, look at this. This is the blue line. This one is the training loss at lambda is equal to 5. You can see that it saturates very fast. So you have a region of over memorization. Normal grokking is the gray region. Do you see this? This is the normal grokking taking place at what number of steps? Approximately 10,000, 30, 40,000 steps. At 40,000 steps, you would have, or close to 100,000 steps, it would actually saturate, isn't it? So grokking stabilizes at 100,000 steps. But now look at what happens here. Do you see this dark red line, guys? This dark red line, where is it stabilizing? Where is it reaching 95% of its accuracy? It is reaching at just shy of 3,000 steps. So compare 3,000 to 100,000, right? Or even if you take this 30,000 steps, so you can see that the differential is huge, isn't it? So much faster. And then you can see, by the way, they're looking at it with respect to this different hyperparameters, lambda and weight. Sorry, not W is the window size here, window size. And so window size matters. You can find the optimal window size. They found that 100 values, if you store the last 100 gradients, that is good. Then you can also see how it works. The loss varies with optimization step. So instead of accuracy, if you look loss, the training loss immediately catastrophically drops because, well, it has memorized the data. But the validation loss used to be pretty high and reach meaningful numbers again at 30,000 steps. But now, because of this, all of this grokking, this fast grok, look at the red line. Isn't it impressive how well or how quickly it sort of achieves that? Right? So this is the main, we can go after graph in this paper. But the main story is, but then they ask a beautiful question. They say, hey, if the low frequency component is more useful, can we just throw away the high frequency component altogether? Like, for example, in this step, like you notice that when let's focus on this spot. What are you doing? To the original gradient, which contains both the high and the low frequency component, you are adding more of the low frequency component, right? Or we sort of, I caricatured it a little bit by doing this. Where is the thing that we did? High and low, I oversimplified it somewhere. Okay, I forget where I did that. Oh, yeah, here. Yeah, if you notice here, I said that if you imagine that a oversimplified world, the gradient is made up of low frequency and high frequency term, right? The gradient term. Then what we are doing is GT plus the low frequency term up to a lambda is basically amplifying. It is amplifying the low frequency term, but it is keeping the high frequency term, isn't it? Why not completely forget about the next update, GT, T plus 1, let us just say, let me take more size, G, T plus 1. Why not just make it, instead of doing GT plus lambda, the low frequency term, let me just say HT that they put here. Instead of doing that, I mean, actually here, I use the language lambda, LT. Instead of doing that, why not get rid of this altogether? Every time, just keep the smoothing part, right? That's a natural question to ask, and these people ask that question. And what they found is that the high frequency component is not useless. It's needed for learning. If you throw it away, then actually grokking gets affected in an adverse way. And so you have to create. The other trick that these people play is they say that, see, don't bring in your GrokFast algorithm till overfitting has kicked in. I mean, till memorization has kicked in. After that phase, turn on GrokFast, right? Turn on the GrokFast algorithm after that. So they use a lot of tricks. At the end of all those tricks is that they put weight decay, they put this, they put that, moving exponential moving average. And at the end of it, they have squeezed as much juice as they can from this, right? And they have essentially created a good. And by the way, this was the thing I was talking about.
So is it, they talk about average, right? Average low frequency. What does that average mean? Is it?
See, this goes back to signal processing and Fourier transforms, Fourier series. But here's a simple way of thinking. If you have a jittery signal, right? So let me speak of it this way. Suppose I have values that go, let's say, like this, right? At any given moment, I take a window and I average it, right? See, what will be? The average will be something like this. Again, I slide the window forward and I take another average. This average will be here. But do you notice something about the average? If I just keep taking moving averages, it will look like this. But if you think about it from a Fourier transform perspective, Fourier series perspective, this is nothing but the low frequency. One way of getting the low frequency components, right? That's what they're saying. It's just a way of doing it. So this needs a little bit of understanding of spectral decomposition, Fourier series, etc. Very basic knowledge, but yeah, this is how this thing works. And with that, I'll open it up to questions.
Question. Yes. So I'm wondering these heuristics about not turning on the low frequency amplification until after memorization. I mean, these seem to be heuristics that were empirically learned. I'm wondering what your opinion is as to how well those heuristics will generalize to all learning problems rather than the ones that were studied in the paper.
Actually, this is a wonderful question. I hold the same question in my mind. I don't know the answer to. My experience over these years being in research is things that are not backed by theory usually don't hold up in the long term, but they have practical value in the short term. Until somebody finds something better, on a case-by-case basis, a lot of these heuristics can squeeze the maximum juice out. That's the way I would leave it.
Okay, thank you.
As if in terms of the transformer architecture, how does this have an impact on?
This completely, most of these experiments were done with 1-layer, 2-layer transformers. In fact, most of the grokking experiments people are doing with taking the decoder, because these days decoder is so popular, GPTs are all decoder based things. So they take decoders and do that. This is all happening with the transformers. It is happening with transformers, it's happening with LSTMs, it's happening with feed-forward networks. They have observed this to happen just about everywhere. Now researchers are beginning to look outside, and they have seen it in CNN, I believe. People are beginning to now ask, is grokking prevalent outside neural networks itself? What about the classic algorithms? Does it happen there also? So people are looking at it. I don't know the answer. Maybe there's already a research paper that has talked about it. I haven't read that.
And one more question, just an extension of that. So with this sort of GrokFast, does GrokFast actually can be work in a transformer again? I mean, do you need special machinery for that?
Yeah, I would imagine. See, what is happening is this is at the laboratory level. And now the question is, should you use it? See, if you're training small custom models, I would strongly suggest, especially if you don't have enough data and you are seeing overfitting, you have the luxury of compute, why not wait for the grokking moment?
Mm-hmm.
And if you want to wait for the grokking moment, why not accelerate its arrival by using GrokFast?
Mm-hmm.
I have a related question. I didn't read the paper, but my sense is, and maybe another way to answer the question that was just asked, is that, this seems to be a result related to the learning algorithm as opposed to the model. And so what I'm wondering is it relevant to all learning algorithms that use some form of gradient, or is it specific to a specific learning algorithm?
No, see, irrespective of the within the neural network world, irrespective of which neural architecture you take, this is a characteristic of learning itself, the process of learning that you see grokking at some point. That is established because that is one of the things that the OmniGrok paper delves into. It says it is more universal than just, for example, toy data sets or special cases. It happens in real world cases. And it does seem to happen. I think it's the OmniGrok paper, some other papers pointed out that it is there with most neural architectures is there. It's happening.
Well, to clarify my question, is it a result that's related to learning when learning is defined as finding, the minimum with the smallest norm, as in gradient descent, not even stochastic gradient descent, but just gradient descent, in the classical sense. And so I guess what I'm asking is, are there other learning algorithms to which this would also apply?
Oh, so let me rephrase so that this time I get your question. See, all of these are first order gradient descent based methods. There are other learning algorithms, for example, second order methods like Newton-Raphson and whatnot, right? Which, for example, go much more strongly with the Hessian and so forth. Would this grokking phenomenon be seen in alternate learning algorithms also, or is it unique to gradient descent based methods? Did I get your question right?
Yes.
Okay. So I don't know. I don't think people have tried it with other class of learning algorithms, but that is certainly a very interesting question worthy of being investigated. See, the majority of work in neural networks is with first order methods, gradient descent based methods. But if you look at people, for example, the many people who, here's a Prophet's convex optimization here, they all keep saying that, what computers become faster, why don't we also use second order methods, they converge faster. And the practitioners are very wary of that because they say, we have tried it many, many times and the second order methods don't quite work. Because there's a lot of tooling there for first order methods, the gradient descent based methods. Not as much is known or understood or tooling exists for second order methods. We know in principle you can do it, you could use the Hessian and so forth. But in practice, people haven't gotten very good results with it.
Yeah, I mean, I guess this is a question that could also be rephrased in terms of the shape of the solution space, right? Is it a phenomenon that arises because the generalization area and here I'm stumbling because I'm not a practitioner, right? I don't have all the language, but I think it's kind of related to what you were saying earlier about the hyperdimensional sphere and where that sort of Goldilocks region is. That what's the shape of that thing? Is it does it have very steep sides, or is it very sort of shallow? And
Yes.
Might we miss it or sort of skip over it because of the high frequency components of the learning algorithm, et cetera, right?
That's right. I think I get what you're saying, and I think you're thinking the right way. A lot of it is neural networks inherently have obviously non-convex loss surfaces. For the longest time, researchers in AI believed that you shouldn't be doing neural networks. They were written off as dead area, because obviously loss landscape is not convex. Later on, it turned out that not having a convex loss landscape is not so bad. Loss landscape in higher dimensions have very interesting properties, actually. They show, amongst other things, for example, ravines. So there are many minimas. There are many, like all the really true minimas, they don't form a point. They can often form a complete ravine that is flowing through the loss landscape, higher dimension. We are beginning to understand how things work in very high dimensions, and these loss landscapes are in these dimensions. So now the joke is on the other side. The people in neural network community, they joke that the other guys who don't believe in the neural networks, they suffer from convexivitis, because they only want to solve problems in the convex loss landscape. Go ahead, Albert. Yeah.
Yeah, so that's a very question I wanted to ask. For the neural networks are going to take over the world, because now they're going to be really simple to kind of write code, and you don't need the classical algorithm. Right? You just write 4 lines of code, and even with a simple set of GPUs, you can solve big problems.
So Albert is making a point that with neural networks becoming so good, will they not replace the classical algorithms? So I'd like to comment on that. That's an interesting thought. See, there is a no free lunch theorem, which is a mathematical result you can't argue, which says that no one algorithm is always better than some other algorithm, even a simple algorithm, all the time. It's the data that decides. If you look at neural networks today, the simple answer is, for tabular data, a very humble XGBoost or gradient boosting or a random forest or support vector machine will beat neural networks hands down. Right? Neural networks tend to do very well with unstructured data. It's true. Every algorithm has a place under the machine learning sun, one way to put it. But there is an alternative way of looking at it now, which is that neural networks have become smart at generating the code needed to solve it using a classical algorithm. You want the random forest code to solve your tabular data, it will write it for you. So that does put a little bit of anxiety in the minds of programmers, for sure. But what happens there is to be seen.
Asif, there's one, I think today or yesterday, there was on Twitter, there was a post that Andre Karpathy actually wrote sensors and directly connected them to neural networks. No code. Absolutely no code has been written.
Oh, interesting.
So this is totally taking sensor data and absolutely just feeding it into neural networks. I'll try to find that and post it.
Nice. Yes, please do.
But again, I want to go back to the higher, the spectral decomposition. So where all is this intuition used? I'm sure it is used, and that's why Fourier is used in many cases. Can you sort of can you tell how is this intuition is used in another space, and they kind of have borrowed it to apply?
Yeah. See, these transforms, right? These are literally magical beasts. It's like think of Merlin and his magic wand, right? I always look at Fourier transform, Laplace transform as literally magical beast. Imagine that you have a signal, a time series signal, for example, a sound wave. And the Fourier transform, which is just a very simple transform, magically extracts all the harmonics in that soundtrack And
Well,
then you can choose to remove noise. For example, a lot of the noise reduction techniques is nothing but a low pass filter. And in fact, if you think about it very tellingly, this algorithm is nothing but applying a low pass filter to amplify the signal. Amplifying is just low pass filter, right? And likewise, wherever there is signal, see, if you just look at your stereo or your amplifier, you'll notice that there is a way to amplify the treble, there's a way to amplify the bass, right? And when you amplify, what are these? These are all literally doing implicit Fourier transforms and suppressing certain range of frequencies. All of sound engineering is that.
Yeah, and I was going to say, when you look at a stereo and you see the equalizer bars, you know, that are jumping up and down, that's essentially the frequency spectrum of the audio signal, and that's a dual of that signal. It's changing the basis from the time series to the frequency spectrum, and it's a fascinating topic. Signal processing is a very deep and wide topic.
Right. I mean, I still remember my first year of college reading the engineering math and encountering the Fourier transform and the Laplace transform. And I can't just tell you how utterly in love I was with it. Just a beautiful thing. They can do anything. Laplace transform is another one of them. It can convert any differential equation into an algebraic equation. You take the Laplace, the differential equations are hard to solve. And usually kids are taught all sorts of methods in college they're tortured with on how to solve differential equations. And then finally they let the cat out of the bag. They tell you that by the way, if you just took the Laplace transform of that differential equation, it would just become an algebraic equation, a high school problem, I mean, middle school problem. And you go like, what?
And it's related to eigenvalue decomposition. And then you also have, by the way, wavelet transforms, which are sort of the generalization of the Fourier transform, where the functions that you're decomposing into are not just sines and cosines, but
That's right. Yeah, wavelet transform, exactly. Absolutely. Oh, by the way, speaking of wavelets, Andrew, thank you for mentioning that. I must mention that CAN paper that we did a couple of weeks ago. People have re-implemented it using not splines but wavelets very effectively using wavelets. So all of these transforms are just magical things.
Hey, Asif, one thought I have is that I don't know whether it makes sense to think of this gradient as some sort of a reward you're getting in a RL context, and if so, like, can we think of this GrokFast as some variation of the standard reinforcement learning algorithms like Q-learning or something, recasting of that, because it seems similar, at least superficially.
Yeah. So, Karthik, the point that you make is good. It is you're basically rewarding the system by saying, hey, let's amplify your ability to extract low frequencies, like the patterns, the overall patterns or moving patterns. In a way. But having said that, I would not use the word reinforcement, because two things. Reinforcement learning has a special class of algorithms. It has its own mathematics of reward gradient, reward policies. It has its gradients and so on and so forth. Quite a bit of theory there. The other thing is, see, reinforcement learning comes in when you don't have differentiable functions. You have no choice but to do, first you have the gradient in your hand. Directly you're doing it. In reinforcement learning, what you do is you don't have that choice. So you somehow reconstruct a policy function, right? And a reward function. And those functions will have gradients with which those functions will get trained. So even though, from a sort of an ethos perspective, I would say there's some resonance, but in reality, this is not as complex as reinforcement learning. It's a very direct way of finding that component of gradients that really gets the job done faster, and in a way rewarding it, adding it to giving it greater importance. That's the way I would say.
So the embedded within its travel, within the training to validation, is its path, and is to cull that path out, the low pass path, and rewarding that more than the
exactly
than the high. Yes.
Yeah, and that is what this picture does. So what they have done actually is, the beauty of it is dead obvious and simple. Like in hindsight, it begins to feel dead obvious. Can you imagine? They have just really inserted 2 lines of code in the forever PyTorch loop, for example. Right? Everybody writes that simple PyTorch learning loop. And in that, they have just redefined the gradient and then let other things happen on their own. That's all. Right? And at the end of the paper, actually, they give the code. Actually, I should have said that. They actually give you the code somewhere in the appendix. Or maybe it's on their website. No, it's in the appendix. And by the way, this is only, you can read in the appendix are the mathematical details, but you'll realize that if you're familiar with Fourier transform, this will all feel very, very natural to you. Right? There's nothing, the intuition is exactly that. By the way, they show that this works with MNest, it works with QM9, IMDB for sentiments and everything, wide range of practical situations. Now, look at this, guys. Here it is. Do you see that you just replace the gradient with a gradient filter with exponential moving average? That's all. Line 14 is frankly the only real line. And how do you implement that function? That function has a very simple implementation. All you do is maintain a list of prior gradients, and then you do the basic moving average thing. That's all.
By the way, I was under the impression that you could calculate an exponential moving average online without a queue, without a memory either, just by sort of adding the latest, or that you can at least approximate it quite easily without a memory. So I'm wondering if that's just an issue with dimensionality, that you can't do it that way here.
I think this paper is more a proof of concept, and such optimizations may come with time. So if you look, see, one thing they make a point of, this somehow is very reminiscent of how, for example, Adam works, which also uses internally all these moving averages and exponential decay and so forth. Right? So they make it a point that they do it in the optimizers. This step is done with the gradients itself even before it goes into the optimizer. See, optimizer step is line 19. Before that itself, the gradients have been modified, in which the low frequency components have been amplified. That's all. And that's all they do. They say, go use whichever optimizer you want to use. Just do that one little thing for me. Go amplify the low frequency component in the gradient, and you're done. That's it. So that's a big message in this. Grokking can be accelerated if you the gist of the paper is grokking can be accelerated if you can just boost up the low frequency component of gradients treated as a random variable, as a time series variable. That's all. And that is what this picture is saying. And the gist of this paper at the end of it is an elaboration of this picture. All right, folks, we have been going on.